Okay, so I realized that I was going very slow, and I probably will continue to go slow now. But it may be that tomorrow morning I might decide to give a slide presentation. But let's see. To make things faster. But okay, so where I left off was when we were discussing this digression into ADS3 CFT2 as an illustration of the kind of phase transition that one sees in these geometries that are supposedly dual to large N CFTs. So that was a specific example of 3 dimensions, ADS3 CFT2. So let's come back to ADS5 cross S5 and N equals 4 superyoungers at large N. So there's quite an interesting story here, which actually is worth telling, because although a lot of people know about it, there are also a lot of people who don't seem to know about it. So so first let me just write down the parameters that go into this correspondence on the 2 sides. This is quite well known, but let's set the stage. So in the gauge theory, the parameters, the main parameter that we have is actually the gauge coupling square times N, which is what we call the 't Hooft coupling. And in N equals 4 theory, it's very special. This parameter is a truly dimensionful parameter, dimensionless parameter, so it's what we call an exactly marginal. So it's exactly marginal, which means that it doesn't run with energy, so we can tune it to be small or big, and it will, in fact, it will be an interesting question to ask. What happens when we take N equals 4 superyoungers at large N or infinite N and take this parameter to be arbitrarily small? And then vice versa, look at what happens when this parameter is arbitrarily big. How do the 2 pictures differ? Okay, so that's, now what does this parameter map to? This parameter on the gravity side maps to the ADS radius to the 4th power divided by alpha prime squared, where alpha prime is actually what's called the string length squared. Okay, so in order for ADS CFT to work, where we have, in a regime where we have a classical gravity description, we must have that this object is much bigger than 1. This particular ratio is much bigger than 1. So, but let's come back to that in a bit. The second parameter that we have in the gravity side is G string, which is the string coupling constant. And the gauge theory side, the analogous parameter is 1 over N. And G string is related to the Yang-Mills coupling as G square Yang-Mills divided by 4 pi. And then if you use the relation of the Yang-Mills coupling to the 't Hooft coupling, that becomes lambda divided by 4 pi N. So if you're looking at the 't Hooft large N limit, then lambda is kept fixed as N goes to infinity. So in that limit, the string coupling is actually proportional to powers of 1 over N. Okay? So that is the dictionary between the parameters on the 2 sides. Now, as we mentioned, the limit, the large N limit, N tending to infinity limit, implies that you have weakly coupled strings which means that the system is classical. Whatever string theory that lives on ADS5 cross S5, its interaction strength is going to 0, so it's effectively like a classical theory or a theory of classical strings. Now, there is a further simplification, as I said, that occurs when you say that you want to be in a regime where you want to be doing easy things, which means you want to be thinking about string theory in a limit where it becomes classical gravity. And so the classical gravity limit gravity. So this is very important. This was already classical. But classical gravity, as opposed to classical string theory, means that you have to have that the ADS radius to the fourth power divided by the string length scale squared is much, much bigger than 1. So that's, when that condition is satisfied, all you need is the lowest lying or the massless modes on the string are the only thing that contribute, whose excitations contribute. And so in that limit, the fact that you are actually dealing with excitations which are extended objects, ceases to be important. So it's the limit in which you replace strings by point particles, and that limit things reduce to ordinary gravity or supergravity. So this limit, of course, is famously related to the fact that on the Yang-Mills side, we are looking at a limit where the 't Hooft coupling is much bigger than 1. So it's a strongly coupled theory. And so it's this reasoning that goes into all gauge gravity dualities that are built from string theory, that the requirement that you are dealing with weakly coupled strings or a classical theory of gravity or a classical theory of strings, that requires you to take the n goes to infinity limit. The fact that at the end of the day you want to deal with gravity or supergravity and not with string theory requires you to take the 't Hooft coupling to be large. That's generally always true. Okay, so so in this limit, as I said, this is the limit in which 2B string theory becomes type 2B supergravity, which is basically just ordinary gravity plus some scalar fields or some extra massless fields. Right. So the regime. So the way we want to think of this is n equals 4 super Yang-Mills in the large n limit. When lambda is very small, we should think of it as a Yang-Mills theory. When lambda is very big, the appropriate description is supergravity on AdS5 cross S5. So there are two pictures in these two appropriate descriptions for these two different limits. And what we will want to understand is, to begin with, is to understand how these two different limits are compatible with each other, or how the picture of thermodynamics that emerges in these two different pictures can be reconciled with one another. Okay, so we start with large n thermodynamics of n equals 4, and so since we want to do thermodynamics, we want to have a non-zero temperature. So temperature is capital T, and because the theory is conformal to begin with, which means that there is no scale. If I take n equals 4 the n equals 4 theory, n equals 4 is a CFT, and if I just take the CFT in flat space, if I turn on I don't expect anything drastic to happen. It's just a conformal field theory, and you heat it up. It's got no scale to begin with. So if you increase there's no meaning to the temperature, the actual value of the temperature, because there's no other scale to compare it with. So you can either have the n equals 4 theory at 0 temperature or have it at finite temperature when you discuss the theory, when you look at the theory on the plane. And the actual value of the temperature doesn't have any sense. Okay, so because it's a conformal field theory, once you turn on temperature, it's the only scale in the problem. Therefore, all thermodynamic quantities like free energy, entropy, etc., their scaling with temperature is just going to be determined by dimensional analysis. Okay? There's nothing more that determines. So, for example, if you calculate the free energy of this theory, so let me make this point clear that so on flat space, all thermodynamic observables depend on T as dictated by dimensional analysis. There's nothing non-trivial that's going to happen as a function of temperature, really, because there's no scale. But it's still worth exploring this because there are some famous results which already have been mentioned in this context. So for example, if you calculate the free energy density, what you know is, first of all, since you have the theory on an infinite volume in flat space, you can't define the free energy. You have to define the free energy density, so per unit volume. So you know that the theory has the theory is it's SUN gauge theory and the large n limit. And if you go back and look at how the large n limit actually works, the scaling of the large n limit works, the classical action of the theory scales of Yang-Mills theory, the large n limit scales as n squared. So there are basically n squared degrees of freedom in the theory. So the free energy density has to scale like n squared. That's a given. Dimensional analysis tells us that this is dimension. This object is an energy divided by a volume, so it has to go like e to the 4th. Okay, and then the only other thing that it can have non-trivial dependence on is the 't Hooft coupling. So that's the only dependence that you can have in the free energy, nothing more. So all you can expect is that the free energy goes from some value at small 't Hooft coupling to some other value at large 't Hooft coupling. And by convention, sometimes it's customary to put that normalization factor pi square over 6. Why pi square over 6? Because if you take the free n equals 4 theory, which means you take the theory at lambda equals 0 and you calculate what is the finite temperature free energy, then F over V is basically just computed by taking all the vacuum bubble graphs. So you compute all these kinds of graphs, sum over all the species, all particle species, which means you have bosons and fermion fields in the theory, so you sum over all the physical degrees of freedom, and what you will find is that this answer is simply minus n squared t to the 4th times pi squared divided by 6. Okay, so that's basically a classical calculation because it's just ideal. You're basically just computing the free energy of an ideal gas of non-interacting particles. That you can find in a standard textbook in statistical mechanics. So I'm not even going to bother trying to explain where that comes from. So all that goes into that calculation is that there are 8 bosonic degrees of freedom in the 8 bosonic fields and 8 fermionic fields. 8 bosonic because there are 6 scalars and the gauge field has 2 physical degrees of freedom, so that's 6 plus 2, 8, and there are 8 fermionic degrees of freedom. So you can put all that together and find that that's the free energy. So that's just classical ideal gas. Okay, so that means that f of lambda is 1 as lambda tends to 0. Okay, so how do we understand the physics at large lambda? So for lambda much bigger than 1, we have to now look at the other description, which is the classical gravity description. So we want to look at gravity on AdS5 cross S5, and we want to look for a solution that asymptotes now. So you want a geometry with conformal boundary given by R3 cross S1. Okay, so we started off by thinking about n equals 4 theory in flat space, then we switched on a temperature, and then as usual we go to the Euclidean formulation, imaginary time formulation, and then in the imaginary time Euclidean formulation, if you want to study static thermodynamic quantities, then the time direction is compact with periodicity given by beta, and so what you're really doing is studying Euclidean theory on R3 cross S1, and so you want a geometry with that as the boundary. Okay, so the corresponding geometry is basically given by, so just like analogous to the three-dimensional example, in this case, if you want a geometry with that as boundary, there is actually an asymptotically ADS5 black hole. And that is again in Euclidean signature. Okay, and I'm not writing the S5 part of the metric because the S5 comes along for the ride for most of this. So what is this function f of r? So f of r is r square minus rh to the fourth divided by r square, and it's worth mentioning that this is the so-called planar ADS5 Schwarzschild black hole, often referred to as the ADS5 black brain solution. And the reason it's called the planar one is because if you look at the constant r slices, again, the constant r slices are R3 cross S1. Okay, so in particular, the horizon of this black hole, which occurs when f of r vanishes, the horizon is at r equals RH. So the horizon is actually an infinite plane. So it's a limit in which you're looking at a black hole which is whose horizon is actually the plane. So this is the ADS5 black brain solution. Okay, also called ADS Schwarzschild in the planar limit. So so this metric, again, you play the same game. What we don't know here is how the size of the horizon coordinate r equals RH, location, how it's related to the temperature. We don't know that, but you can figure that out again by doing exactly the same exercise that we did this morning, which is requiring smoothness. The fact is that this circle, thermal circle, again shrinks to zero size at the horizon because it's multiplied by this function that vanishes. So smoothness at r equals RH implies that again T is given by f prime of RH divided by 4 pi, and if you work it out, that means that RH equals pi times the temperature. Okay, so for this black brain solution, as you increase the temperature, the horizon size increases. So it's RH is just proportional to the temperature. So now once you know how RH or the horizon coordinate, the location of the coordinate depends upon temperature, you can calculate the entropy, actually the entropy density. Okay, because the horizon is infinite plane, you can't really define an entropy because that diverges. You need an entropy per unit volume. So the entropy density is calculated again as before by the Bekenstein formula. So which means you calculate the area of the horizon, horizon area in 5 dimensions. So the entropy, or entropy divided by the volume, 3-dimensional spatial volume, which is the entropy density, little s, is given by the horizon area in phi d divided by 4 times Newton's constant divided by the three-dimensional volume. So all of this is just, I'm just trying to make it explicit. But at the end of the day, the result is just that this is given by RH cubed. Note that the horizon is actually a three-dimensional surface. It's a three-dimensional plane. And so its area is given basically by the value, so when you calculate its area, you need to calculate the volume. When you calculate the volume, you get R evaluated at RH cubed. So that's roughly like the radius of the horizon, so you have to do that. So you get an RH cubed, and then you have an L square ADS, and this will probably be the last time I will write the L square ADS. For all practical purposes, we can set this to 1. And I did that this morning without actually saying so explicitly. So that's the result. And so at the end of the day, this, if you use that equality, this is proportional to pi cube p cube divided by 4 times Newton's constant. And I'm going to just set LADS equal to 1. Okay. Now, given this entropy density, it's now straightforward to calculate the free energy density. You calculate the free energy density by just recalling that S is minus dF dt, and then this then implies that since we know the entropy density, we now get the free energy density, trivial integration, and we just need one extra bit of information, which I can explain later, is the dictionary between G and n squared, and that's actually easy to figure out, but I just write it down here. 1 over 16 pi G is actually n squared over 8 pi squared. Okay, this tells us that this tells us that the Planck scale effects in gravity side are related to 1 over n effects in the gauge theory. It's a relationship between quantum gravity effects in the bulk and 1 over n effects in the boundary theory. Okay, so if you use this dictionary, then the free energy per unit volume just comes out to be